There are a couple more angle properties that we're going to talk about which happen outside of the circle as opposed to inside, which are the ones that we just did in our last video. So the ones that happen outside the circle are all going to be the same exact formula, which is really nice. So I'll show you what they look like, and then we'll look at what the formula is. So I'm going to draw all three. So you're going to need to have three circles here. So one of them happens when you have two secants that intersect outside the circle. They keep going. I just don't want to draw them forever. So this would be one where you have two secants. You could have, you could have two tangents in a circle. So two tangents in a circle, remember, a tangent touches the circle just in one place. So if I do that, I have a tangent here maybe, and then a tangent here. And again, they go forever. I just don't feel like drawing them forever. So this would be if there were two tangents. And then my other possibility is that there's one secant and one tangent. So if I look here, I've got one secant and one tangent. Again, they go forever. So the angle that I'm going to be looking for in all of these cases is this angle here that's on the outside. Remember, we use theta, T-H-E-T-A, because it is like the x of angles. It's our variable where if we want to find an angle, that's what we use for the variable. We use it in trigonometry. We use it in circles. So I want to get us used to using that. So this circle here I didn't write it, but it was one secant and one tangent intersecting in a circle. So the property is going to be the same for all of these. And we're going to be looking for this angle here on the outside. So here, here, and here in this other circle. So I'll show you what that property is going to look like. I guess we can do it with one of the circles first, and then just extend it to all the other circles that we have. So if you have two secants in a circle, essentially you take the big one minus the little one, you divide it by 2, and then you get this angle. And so I'll write this out. What I mean by the big one, I've got a big arc, and then over here I've got a really small arc. So if you take the big arc and you subtract the small arc and you divide that by 2, you will end up with that angle that's there on the outside. And that is the same for all three of these. You take the larger one, you subtract the small one, you divide it by 2, and you're going to end up with that angle on the outside. So that's true for all three of them. If I look at the two tangents example down here, I've got a big arc right here. It goes from here to here, so it's large. It goes all the way around. And then I've got my small arc right here. I divide that by 2, and I end up with this angle. I can also do that with this one over here, my one secant, one tangent example. I've got a big arc that goes from here to here. And then I've got my small one that goes from here to here. So if you want to put letters on that because that makes more sense to you, we can do that. In this case right here, I could I'll make my big arc the same in all three of them. So I'll have this be A and B. And I'll have my small arc be C and D. Which means in this lower one, my big arc would be A and B. This one's a little bit tougher because the small arc is A and B as well. It's the minor arc here, and then the major arc is the big one. The one secant, one tangent example, you have A, B, and then I have C. There's only 3 in this case. So we could write them out for all of them if you want. I'll do that here. You can skip ahead if you don't want to. Look at the description, and then you can see what we're going to do for this last one. But to write them out for each individual circle, if you want to see what that would look like. So I've got the measure of AB minus the measure of CD over 2 equals the angle. That would be the formula for this one. Again, big arc minus small arc divided by 2. It's the same for all three of them. So in this case, you'd have the measure of AB. Now, in order to do this, really, in order to label this correctly, we need another point out here. Because if we don't know whether we're talking about the larger one or the smaller one. So I really should say ACB. So I've got the measure of ACB minus the measure of AB divided by 2, and that's going to equal the angle. So equals the angle. And then in our last one, it's the same thing. It's the measure of B. I need another one. So D. So the measure of BDC minus the measure of AC right here. Divide that by 2, and you end up with the angle. So big arc minus the small arc divided by 2. This is how I do it, and this is how I remember it. It's way easier for me to just remember this one formula and just know what the big arc and the small arc look like. All right, the last one that we have here is a bit of a different property, and it has to do with other properties and stuff outside the circle. So it's on the circle. It's not exactly outside the circle, but one of the segments looks like it's outside the circle. Sort of looks like this. This is another example of one secant in one tangent. It's like half outside, half inside. So I wanted to show this to you so you can see what that looks like. So this angle here, and I'll use a different angle because we've used theta the whole time. Remember, this is the angle phi. It's like an O with a vertical line through it. It is an inscribed angle. I know an inscribed angle we said was before usually that it doesn't involve a tangent, but this is like has the same properties of an inscribed angle. So it's got the same properties as an inscribed angle, which means that it's half as big as the arc that it opens up to. So this arc, we'll call it G H I. This angle right here, phi, is equal to half of the measure of the arc GHI. In my circle, I can't quite tell if it's a minor arc or a major arc because I haven't drawn the center, but so it's going to be half as big as well. And so I put this in the outside section because like it's sort of outside, but it's sort of inside. And anyways, that's one last property that we have.